Hi everybody, welcome back to the Feynman technique. Today I've got this is a pretty complicated integral, and of course we will be solving it using Feynman integration. Of course we'll be using other techniques also like complex numbers, but let's just go ahead and get into it. So the first thing we want to realize here is that cosine of natural log x can be expressed as the real part of x to the I, and I'll show that really quick. So if we have x to the I, um, we can express this as e to the natural log x to the I. And I know I've already shown this on this channel, but for those that don't watch the channel, for every video, I'm going to show it again. So we can write this. All right. And then the next thing we can do is using the properties of logarithms, we can bring this I outside. And then we can use Euler's formula, e to the I theta is equal to cosine theta plus I sine theta to get this. This is equal to cosine, well, our theta is natural log x plus I sine natural log x. And then you can see if we take the real part on both sides, this imaginary part right here will drop out and we'll just have real part x to the I is equal to cosine natural log x. All right, so what that allows us to do is rewrite our original integral by replacing this cosine natural log x with the real part of that. Now, we can bring the real operator right outside the integral right there. So it's just going to be the real part of this integral. All right, so now what should we do? Well, let's see. What's messing us up here is this natural log x. So let's see if we can find a different way to recover. We'll start with something simpler and try to recover that natural log x. So what we're going to do is we're going to create a function of t that's equal to the integral from 0 to infinity of x to the t over x squared plus 1 dx. Okay. And then let's see what happens if we take a couple derivatives of this. Well, f prime of t is going to be equal to the derivative with respect to t of our original function of t, and we can use the Leibniz rule for differentiation under the integral sign to bring the derivative right inside. All right, and then taking the partial with respect to t of that is just going to give us x to the t natural log x over x squared plus 1. All right, and then we can go one more derivative. And we can say, let's see, if we took another derivative, all that would happen is we would recover another factor of natural log x. And this is f double prime of t. Okay, so now, given that, we can say that our original integral I is equal to the real part of f double prime evaluated at I. If we evaluate f double prime right here at t is equal to I, this t becomes an I, obviously, and then we take its real part and we have exactly our target integral. So I is equal to the real part of f double prime at I. So now we need to find a new way to write this. And we can use a formula that I derived on a previous video. I will link to it in the description if you want to see it. We can rewrite, there's actually a formula for this. And I'm going to paste it here right now. So the formula is this. I'm not going to state for what values this converges. That's beyond the scope of this channel. Needless to say, it is going to converge for the values that we need it to converge for. All right, so let's go ahead and use this formula and see what we get. Well, this implies that this part, not this part, that this is equal to, well, we're just going to take this and replace the appropriate values for a and b, we can see that our a is actually t. So we just put a t in there for a, and our b is 2. Great. Oh, sorry. T, yep. Okay, so that's true. So what we can say now is that f of t is just equal to this. Great. Okay. Let's see. What do we do now? Well, we don't want f of t. We want f double prime of t. So we're going to need to take 2 derivatives of this. Now, this is kind of a nasty thing to take a derivative of, but it's a very mechanical process. And if you know how to take derivatives, you can take 2 derivatives of this. So what I'm going to do is I'm just going to skip to f double prime of t, and I'm going to set it equal to whatever online integral calculator says the second derivative of this with respect to t is. So I'm going to pause the video and I will paste the derivative there in a second. All right, we're all done, and this is what online integral calculator gives for the second derivative with respect to t of this function right here. All right, so now that's an extremely nasty function right there. But you know, this channel is about the process, not the nitty gritty details. But anyway, this is our f double prime of t. So now we just use this right here, that I is equal to the real part of f double prime at I. Well, that's equal to the real part of, this is our f double prime right here, and we evaluate that at the point I. Okay, and now, I mean, that's it. We're done. Um, I am not going to go through the process of taking the real part of that, but I'll go over some of the tricks we can use. Um, well, first, what we need to do is recognize that this can be split up into I pi over 2 plus pi over 2. And we can use a trig identity for that, where we can use the sine x or sine theta plus pi over 2 identity to express this in terms of cosine of an angle. Likewise, we can represent this as 1 minus sine squared of the thing. So really all we need to do is find sine of this thing using the trig identity sine theta plus pi over 2. Then split this up into 1 minus sine, and we can replace all of our expressions like that. And then, of course, we're going to have to use Euler's formula again to actually split this up into a real and imaginary part, and then just eliminate the imaginary part. But I'm not going to go through that whole process. That's not what this channel is about. What I'm going to do is I'm going to pause it and plug this into a calculator to show what we get. Calculation's done, and this is what it turns out to be. So the real part of this expression right here is this. That is a very nasty, nasty answer. However, it is expressible in terms of elementary functions. So, very, I mean, messy but satisfying answer. This integral right here converges to a value that is expressible in terms of pi and e. All right, everybody. I hope you enjoyed that, and we'll see you next time.